Hello, myself Muhammad Tajuddin from 324 group. I am here to explain the topic transport of charged particles through membrane in the book Biophysics written by MV Volkenstien. So let's start. The electron conductivity of cell membranes is about 10 to the power minus 3 milliohm centimeter square. After the artificial lipid membranes, it is much lower. In order to 10 to the power minus 8 milliohm centimeter square. These values many orders of magnitude lower than the electric conductivity of potassium chloride in water, which is equal to 10 to the power 4 milliohm centimeter square. So this figure which calculate the energy of ion membrane. In the figure A, the effect of its image shows that the effect of the image forces, in the B, formation of ion pairs, and in the C, hydrophobic 4 in the membrane, and in the picture figure D, the effect of complex formation. The low ionic conductivity of lipid membrane, which is treated as homogeneous medium, is determined by the law of dielectric constant of lipids. This data being unfavorable in a cooperation of charged particles. The distribution coefficient of a particles between lipid and aqueous phase is equal to exponential of minus W by RT, where W is equal to energy, R is Reynolds constant, and T is the temperature. The first term of principle 1 for the spherical particles of a radius A is equal to W is equal to Q by A into 1 by epsilon minus 1 by epsilon W, where Q0 is equal to x square E square by 2 kT, where x is equal to ionic valence, E is equal to charge of an electron, and epsilon is equal to dielectric constant of a lipid. So, if the dielectric constant of the water at temperature 25 degree, x is equal to 1, q0 is equal to 28.2 nanometer, and if radius is equal to 0.2 nanometer and epsilon is equal to 3, then exponential of minus w by rt is equal to 10 to the power minus 20. The ion energy of ions in the membrane, however, decreases due to at least 4 factors, which is said by Markins, Pashchenko, and Shishmazev in 1977. The 4 factors are: the membrane has finite thickness, ions can form ion pairs inside the membrane have fixed pores of dielectric constant, and the ion can be transported by ionophore. A carrier increases the effectivity of the radius. These 4 factors effective schematically demonstrated in figure 10.9. At the interference between the membrane and aqueous phase, these arise image forces. The electrostatic energy W of ion in the membrane decreases somewhat and assumes the shape of the curve shown in the figure 10.9a. Because of this effect, the energy is decreased by an amount of order of A by L, that is by a few percent. The barrier height is order of 100 kilojoules per mole. The formation of ion pairs does not give a noticeable gain. Either the maximum decrease of the energy is not more than 2-fold. Pores of high polarizability can considerably reduce the energy of the charge of the membrane. At B very less than 1, the energy of the particle at the pore axis is given by W is equal to E square by 2 EPA plus E square by epsilon M by P into epsilon M by epsilon P. The second term in this formula, which is due to image forces acting on the pore walls. The function of Px has been calculated numerically. It's a value of not exceeding 0.25. If epsilon P is comparable with the epsilon W, then the second term Wp predominates. At epsilon is equal to 2, the value of Wp is approximately 1180 by B nanometer kilojoule per mole. The fourth factor is ion transport. So, a number of substances serve as ionophores, carrier of alkene cations. Example are peptidase, cyclic antibiotics, which have been studied in detail in the work of Shemyakin, Ovinskov, Ivanov, and also Pressman and co-workers. Another group of carriers has also been mentioned. Example, macrotellidase, which are cyclic compounds containing 4 ether and 4 ester linkages. The structure of some cyclic carriers is shown in the figure 10.10. Ionophores are neutral molecules of high polarizability which form a complex spherical complex with ions. The energy of complex in the medium is given by Wc is equal to epsilon square by 2 epsilon m into B plus epsilon square by 2 epsilon C whole into 1 by A minus 1 by B. With the high polarizability of ionophore, the second term may be neglected. At B, which is approximately is equal to 0.5 to 1 nanometer at 25 degrees Celsius, WCI, the energy is equal to 69.3 to 34.4 kilojoule per mole. So, the ionosphere can considerably lower the barrier to the ion penetration. Direct measurements of the temperature dependence of ion transport by membrane in the presence of ionosphere have demonstrated that the ion transport obeys the Arrhenius equation. Arrhenius equation is G is equal to A into exponential of minus H by RT. H is equal to enthalpy. The enthalpy of activation is H plus is equal to 136.5 kilojoule per mole for a monocation, 231 kilojoule per mole for varenicline, and only 39 kilojoule per mole for gramicidin A. Monactin and varenicline are mobile carriers, while gramicidin A forms a polar pore in the membrane. In the presence of varenicline and monactin, the conductivity sharply decreases when the lipid membrane is being frozen. No such effect is observed in the presence of gramicidin A. The transport facilitated by the formation of pores is sequential pores. A pore can be formed by several successively arranged molecules between which the transport of ion takes place. The ion can be transported not by one but simultaneously by several ionosporic molecules. This is a cooperative mechanism. Various mechanisms of induced ion transport are shown schematically in the figure 10.12. As has been pointed out, membrane transport may be associated with presence of King's mobile structural defects in the liquid crystalline phase. The possibility of interpretation of this kind of effects on the basis of theory dislocations have not yet been completely exhausted. While discussing the membrane transport of univalent cation, we have closely approached the problems pertaining to excitability of membranes, to the generation and the propagation of the nerve impulses. So this is a small topic. That's all. Thanks for watching. Thank you.